Welcome back, friends, to another session of fluid mechanics and rate processes. So, we have been looking at similitude and modeling, and we will continue on that. We explained in the last class what does similarity mean. So, I will go through that again a little bit, and then today we are going to understand that with the help of a few examples. So, I hope by now you have got a fair idea of what is the meaning of these two words in this phrase, similitude and modeling. So, as the name suggests, similitude refers to similarity. Okay, how do you make flows similar? So, we understand that, and then how do you model using these similarities to get the desired results? Okay, so that whole thing is very important from an engineering perspective. So, in the last class we were looking at an example that suppose you have CD as a function of RE. Okay, that means the drag coefficient on a body could be non-dimensionalized as CD. So, this is the non-dimensional drag coefficient, and we have taken the example of an airplane, and RE is the Reynolds number, which is another similarity parameter. So, we showed that drag could depend on many parameters, but suppose we took a special case that the shape of the aircraft is fixed, we are not worried about the altitude effect. So, we are flying at sea level, we are not interested in the surface roughness, we have a reasonably smooth surface. There are no free surfaces, we are not interested in the effects due to gravity and so on. Then the CD would depend only on RE. And then we tried to understand using this idea the concept of similarity. So, if we want to look at similarity, the first thing was geometric similarity. And this means that the shapes are similar, in fact shapes are identical, but the length scales are related to each other by a constant scale. So, if I had, let us say, a rectangle in the model and in the prototype, then it is rectangular shape in both of them, and the length scales for the width and for the length of the rectangle would be in the same proportion. If the geometric similarity is ensured, then we can talk about dynamic similarity. And this is if all independent pi's are identical in the context of a model and prototype, then the parameters for dynamics such as forces, like drag, etc., are also similar. So, to illustrate this example, what we can do is we can talk about a model and we can talk about a prototype. So, suppose I have an aircraft where I am doing some testing, and let us say this is the length of the model, and maybe I have a prototype which is probably larger, and this is the length of the prototype. I had speed of um here, I had a speed of up here. Okay. and dm, let us say, is drag on model, and let us say dp is the drag force on prototype. And because I have assumed that CD is only a function of Reynolds number, so the first of all I have to talk about geometric similarity. So geometric similarity would imply that if my scale factor here is Lm and Lp, the ratio of those, then all the dimensions, the remaining dimensions, should also follow this scale factor. All the angles should be identical, all the shapes should be identical. So that would take care of geometric similarity. Dynamic similarity is going to be ensured, so the flows are going to be dynamically similar if Reynolds number for the model is same as the Reynolds number for the prototype. Okay, which would actually imply that if I am doing my experiments in the air just like in the prototype, then Reynolds number for the model would be rho of the air that I am going to use for the model times the velocity, so u of the model, and the length of the model divided by the mu of the air, the viscosity of coefficient of viscosity of the air for the model. This should be exactly same as rho p up Lp divided by p. Now if the medium is same, so if I use the same fluid, then of course the rho and the mu are identical for the model and prototype, and automatically you would get um times Lm is up times Lp. So what this tells me is that if I had to conduct experiments, let us say for a model aircraft, suppose this was a 1/10th scale model. Okay. So original aircraft is 10 meter long, and suppose I make a model which is 1 meter long. Then I know the Lm and Lp relation, and from this I can estimate that if my prototype was flying at, let us say, 40 meter per second, what should be the corresponding speed for my model to ensure that they are dynamically similar, which would occur if the Reynolds number are similar. If that happens, if I am able to ensure that the Reynolds number are identical, then I would have ensured the following. This would ensure that CD on the model is identically equal to the CD on the prototype. Okay, which means that if I knew the drag, so what is CD? CD would be the drag on the model divided by half rho, because I have non-dimensionalized it, with and maybe the length square, which represents an area for the model, and this would be equal to the drag on the prototype divided by half the density of the air I use for the prototype, the velocity or the speed for the prototype squared times Lp squared. Okay. And if I make measurements by doing experiment on the model, then I will be able to measure these, the drag on the model, and because I know everything else now, I can estimate what would be the drag on my prototype. Okay. So you can see now the relationship between similitude and modeling. Okay. So to get the right kind of modeling, I must look at the right kind of similarity and the right kind of similar parameters. Let us look at some examples. So the first example that I would like to present to you is that to estimate the power requirement of an airship traveling at 10 meters per second, it is proposed to test a 1/20th scale model in water. What should be the testing speed? And the prediction rule for power. Okay. All right. So what is being suggested is that there is a model which is going to operate in water, and there is a prototype which will operate in air. So let's list the parameters, and then it will help us in doing the analysis. So the length, for example, the model has a length Lm, which is going to be 1/20th of the prototype. So I am simply going to write that the length of the prototype is Lp. We have not been told what is the length of the prototype. Okay. The speed, I have the u of the model, which I am supposed to find out, and the u for the prototype is 10 meters per second. Rho is the density. So the rho for model in water, so I am going to write down the density of water, that's 10 to the third kilogram per meter cube. But the prototype operates in air, so this is going to be 1.226 kilogram per meter cube. Let's look at the viscosity. The viscosity of water is 1.14 into 10 to the minus 3 SI units, which is Pascal times second. And the prototype operates in air, so I am going to write down the coefficient of viscosity for the air, which is 1.78 into 10 to the minus 5 Pascal second. Okay. So let's see what are the important parameters. What we have been told is that there is no free surface, okay, because this is completely submerged. So in fact, when we do the experiments of the model of an airship in water, we have to make sure that it is submerged deep into the water and there is no effect of free surface. So we keep that in mind. We also know that there is no cavitation. If there is any, we will ignore it. Okay. So therefore, Euler number is not important. There is no free surface. So Froude number is not important. And we will also ignore the effect of gravity. So therefore, we will assume that only the Reynolds number is relevant. Essentially, the ratio of the inertial forces and viscous forces. So we will try to match the Reynolds number for the two studies. Okay, so we match the Reynolds number. So Re for the model is same as Re for the prototype for similarity. Geometric similarity has already been ensured. So if I want to do dynamic similarity, I must ensure Reynolds number must match. So that would imply that rho for the model times the speed for the model times the length for the model divided by u for the model should be identical to rho of the prototype, u of the prototype, L of the prototype, and mu of the prototype. Okay. This, of course, the modeling takes place in water, and for the prototype, the medium is air. So I have listed everything over there. So by putting in the relevant quantities, we can now estimate what is the u for the model, and that you can see would be rho p divided by rho m times Lp divided by Lm and times mu model divided by mu prototype times u for the prototype. And I can plug in now the relevant numbers, and this would be 1.226 divided by 10 to the third. Okay, density of air, this is density of water, and I already know the scale of the prototype to the model, it's a 1/20th, so that number becomes 20 here. And then the viscosity, so for the model it is 1.14 into 10 to the minus 3, and for the prototype it is 1.78 into 10 to the minus 5, and the u prototype is 10 meter per second. The airship is traveling at 10 meter per second, and that would work out to 15.7 meter per second. Okay. So therefore, to do the experiment to ensure dynamic similarity, which means to ensure the same Reynolds number, I will have to pull the model of the airship in water at a speed of 15.7 meter per second, okay, which is larger than the actual speed of the airship, which is only 10 meter per second. So that finishes the first part of the problem about the testing speed. Now for the power. Okay. So as you know that power is drag times the speed. This is, so I must estimate the drag. So drag is given as CD times half rho u square and L square. So this is my dynamic pressure, and this is my area. Okay. So CD is a non-dimensional quantity, drag is in Newton, so I have non-dimensionalized it with a dynamic pressure and then a quantity which is area. This could have been an area related to the cross section area, the surface area, the projected area, but I have just used a area here which is L square. So if I look at the drag on the model, that would be CD on the model times half rho model u model square L square. And if I look at drag on the prototype, then that would be CD for the prototype half rho prototype u prototype square and L prototype square. Okay. If I want to get the power, then I would have to multiply both these expressions with velocity. Okay. So if I want to get power on the model divided by power on the prototype, then that would be dm times u model dp